Okay guys, this is the last video here in the solubility series covering multiple equilibrium, and this applies to systems of chemical equations where you have two or more simultaneous reversible reactions occurring. So I'm going to walk us through a few examples of those. We'll do at least one calculation, and then at the end what I wanted to do was to go through in more detail the qualitative aspects of multiple equilibrium, which you're going to have on your assessment for the solubility chapter. So here's an example relevant to environmental chemistry. Here on the left we have a healthy coral reef, and on the right hand side we have a dead coral reef. Coral reefs, the backbone of the coral reef is the calcium carbonate, which is sensitive to the acidic content of the ocean water. And in this first equation, what we're looking at is the relationship between gaseous CO2 and dissolved CO2. And as the partial pressure of CO2 in the atmosphere increases, this drives more CO2 into the aqueous phase. The aqueous CO2 then reacts with water to form carbonic acid, and then the carbonic acid forms hydronium, and then the hydronium negatively impacts the health of the coral reef. And so you see that you have multiple equilibrium participating in the same system, and that's what this section explores. So here's another example more relevant to our own health. Here we have the main mineral involved in tooth enamel. We have calcium ions, phosphate ions, hydroxide ions. This is generally very insoluble, but of course it does dissolve a little bit. So you'll have these ions in equilibrium with the tooth enamel. And what can happen if you eat acidic foods, this conjugate base here, which is fairly strong, will react with the hydronium. The hydroxide, of course, will react with the hydronium in acid as well. And so you'll wind up consuming these species if you have too much acid for prolonged periods of time. And what that will do is it will cause the enamel to shift. It'll cause this first equilibrium to shift towards the right. And so you wind up over time having decay of the tooth enamel. How fluoride protection works. Essentially, you replace the hydroxide with the fluoride, giving you a mineral that doesn't dissolve as easily in acidic solution. And so this is the basis of fluoride protection. However, of course, too much fluoride in your bones can also lead to health problems, and so there's a balance. So here we've got an example problem where we're being asked to calculate the concentration of ammonium ion that is required to prevent the precipitation of magnesium hydroxide. And the magnesium hydroxide and the ammonia concentrations are set, and so these are the equilibria that are at work here. We've got the dissolution reaction involving magnesium hydroxide. We essentially want to prevent this reaction from precipitating. The other reaction at work here is the base dissociation reaction for ammonia. Here, ammonia grabs a proton from water. That forms the ammonium. That's the concentration we're trying to find, and it gives us some hydroxide. And so we see that these two equations overlap with the hydroxide ion species. So the first thing that you want to calculate is what would be the minimum amount of hydroxide that would lead to precipitation. And so we use the KSP expression for magnesium hydroxide for that. We know the magnesium ion concentration, so we can solve for that hydroxide concentration, 1.2 times 10 to the minus fifth. If the hydroxide concentration goes over that value, then you're going to start to see precipitation of the magnesium. So if you want to see that occurring, then if you want to prevent that precipitation from occurring, then you need to keep the hydroxide concentration below that value. Now, how do we control that? Well, we have the other reaction here. which involves a Kb expression. So you've got Kb equals the concentration of ammonium times the hydroxide concentration divided by the ammonia concentration. If you add ammonium, what that is going to do is it's going to shift this reaction to the left, which will end up consuming some of the hydroxide in the system. And that's what you want to do. If you want to keep the hydroxide concentration at a minimum, you need to add a certain amount of ammonia to keep the hydroxide concentration at that level. And so that's what we do here. We rearrange the Kb expression. We already know the ammonia concentration. We know Kb. We know our minimum hydroxide concentration. And so what we can, or our maximum hydroxide concentration. So what we can do is we can use that to find what would be the minimum ammonium concentration. And so we substitute in the hydroxide concentration from here, substitute in the ammonia concentration in Kb, and we find this value of 0.15 for the concentration of ammonium. You need to keep, I may have got the minimum and maximum labels mixed around. In any case, this is the maximum value of hydroxide that you can have. If you have any more than that, you're going to form a precipitate. And so what you want to do then is find what is the minimum value of the ammonium that will keep the hydroxide concentration at that value. And that's this number here. So if the ammonium concentration falls below that value, then the hydroxide concentration is going to be above this value, and that would cause precipitation. Here's an example problem that's very similar to that one. I'll leave this as an exercise to you. There are other interesting problems to work through. They're somewhat tedious because they're a bit involved, and so I'm not going to work them here in this video. What I'm going to do is focus on this problem here, which is more qualitative and more relevant to the assessments that I'll be giving you over solubility. So in this problem, we're considering an equilibrium reaction between magnesium hydroxide and its dissolved ions. And what we want to do is to be able to predict the effect of adding these different species to this equilibrium mixture. And we want to know what's going to happen to this equilibrium. So first off, we'll start off by adding solid magnesium chloride to this reaction mixture. And what happens when you take solid magnesium chloride and you dissolve it in water? It dissolves readily, so you're going to be forming magnesium cations and chloride anions. There you're going to have an ion in common with the magnesium, okay? And so that's going to increase the concentration of the magnesium, which is going to push this reaction to the reactant side according to Le Chatelier's principle and the common ion effect. And so that is going to make the magnesium hydroxide less soluble by adding this species. What happens when you add a strong base like potassium hydroxide? Potassium hydroxide dissolves readily and you get hydroxide ions in solution. We have another common ion that's going to increase the concentration of the hydroxide. It's going to shift this reaction to the left. Again, you're going to be making the magnesium hydroxide less soluble in a strong base solution. Conversely, what would happen if you added an acid? Well, that's equivalent to adding hydronium to the system. The hydronium will react with the hydroxide, consuming it, so you'll be decreasing the concentration of the hydroxide in the solution, and that is going to tilt this reaction to the right. So adding an acid would make this magnesium hydroxide more soluble. Lastly, what would happen if you added solid sodium nitrate? Well, if you added solid sodium nitrate, you'll be forming sodium ions and nitrate ions. However, neither of these species are in common with those. They do not undergo reactions with either of these species, and so therefore there will be no effect on the equilibrium if you add solid sodium nitrate. I guess one more one more reagent to consider. What would happen if you dropped another chunk of the solid magnesium hydroxide in there, right? So you're increasing the amount of magnesium hydroxide. Well, you're not increasing the concentration of the magnesium hydroxide because it's a solid, right? When you increase the number of moles of magnesium hydroxide, you also increase the volume of that magnesium hydroxide sample. So you can think of the concentration as being fixed. It doesn't change. And therefore, if the concentration of a species doesn't change, then the equilibrium will not be affected. So when you add the solid, there's no effect on the equilibrium. It depends on what solid you add. When the solid is one of the reactants, it doesn't affect the equilibrium. But you can add solids that dissociate and form ions, like we've seen in this example, and those do affect the equilibrium. We'll go through another example here of this. Like I said, there's going to be several questions like this on the exam, predicting what happens to equilibrium. So here we will consider the dissolution reaction for nickel 2 carbonate, okay? And we want to know what's going to happen if we add these reagents to it. So in the first case, we're adding some solid reactant. And as we just discussed, adding the reactant, which is the solid, to the equilibrium mixture is not going to affect the equilibrium in any way. So there's no effect when you add, oh, I'm sorry, I misread the compound. It's not nickel carbonate, it's nickel nitrate that we're adding. And I also have a typo here. You see the subscript 2 here. That should also appear there as well. So I'm mistaken. The nickel nitrate will be completely soluble. So you're going to be forming nickel ions in solution and nitrate ions in solution. And if you increase the concentration of the nickel ions, that is going to push this reaction to the left. It's going to make the nickel carbonate less soluble. What about if you added a potassium perchlorate? Well, you're going to be forming potassium ions and perchlorate ions in solution. Neither of these ions have anything in common with the products over here, and therefore there won't be any effect on the equilibrium. So part B would not affect the equilibrium at all. What if we added an acid like nitric acid? So here, let's see. So they give us a hint. The nitric acid reacts with carbonate ions to produce hydrogen carbonate and water. And so the trick here is that this ion will react with the acid. So this is a fairly strong base, so it's going to react with the acid to form the weak acid anion. That's going to effectively consume some carbonate, and that will cause the nickel carbonate to become more soluble when you add an acid. So this is the type of thinking that you need to execute on some of the multiple choice questions on the exam. You have to be able to predict what's going to happen when I add a particular reagent. So you have to be aware of acid-base reactions. You have to be aware of the common ion effect. You have to take all of the conceptual things that we've been learning about and then apply them in this sort of fashion. So that should be the last slide. So I'm going to end this video here.